There we go. So today's topic is about finite impulse response filters, FIR filters. And this part, what we have done is first we have the first exercise was about creating signals, all sorts of signals, test signals, whatever. The second one was basically how to create a system. Third one, which has the deadline today at noon, actually was about responses. So practically, first the impulse response, and then from impulse response, actually you can derive the frequency response. Okay, which is simply the transfer function evaluated at the unit circle. Okay, today's topic is basically looking closer at the finite impulse response systems and how we can do filters based on the this finite impulse response. The nice part of the FIR filters is that by default, well, not you can actually make also nonlinear phase response, but it's quite easy to do a linear phase response with the FIR systems. You just need to have symmetric impulse response. Symmetric meaning basically symmetry around origo, either positive or negative symmetry. So either these are exactly the same, or the left and right side are mirror images. Either or, that will actually end up having the linear phase response, and that's the whole thing about the finite impulse response systems. You can have a better the amplitude response characteristics with IIR systems with less of the parameters, less calculations, but basically the finite impulse response systems are nice since the linear phase response, meaning that these all the frequencies that are coming in will actually have the same time delay through the system. Okay, that's the whole thing. Okay, I'll just quickly go through the fundamentals of how to design FIR system or FIR filter by windowing method. And everything starts from ideal low pass filter. Okay, usually you draw it like that, but remember there's also the negative side. So on the frequency axis, there are also the negative frequencies, which is just 180-degree phase shift. Okay, if we have a cutoff frequency like that, and we would like to get the impulse response for this kind of system, we do just inverse Fourier transform of this, which transforms, if this was basically e to j omega kind of thingy, so the amplitude response of a system, which is simply the Fourier transform of the impulse response, then inverse Fourier transform would give you the impulse response. And in this case, continuous time impulse response. How to make this one sampled system first? Well, easy. You just sample it. Okay, and how to do it finite impulse response? Well, you cut it there, for example. So set the value 0 after those points, meaning mathematically that you are multiplying this function, sync function with a box. So there's a WN, and there's also that sync type function. Sync meaning sin pi x divided by pi x, or sin x divided by x. There are two kind of sync functions in the world. Ask the mathematicians why. Okay, but anyways, that's a sync x is sine, not 2 pi x divided by pi x. Okay, good. So, and that one sampled. And in this case, actually, the exact form of this one, if we have a sample rate fs 1 over ts, practically this one follows the sampled sync function, which is our h of n, follows the sync n times cutoff frequency divided by Nyquist frequency. Where the Nyquist frequency is simply half of the sampling rate. And okay, this is already discrete time, but this would be infinite. We just multiply this one with the this sample window. Okay, that's mathematically exactly this kind of impulse response. Finite, nicely symmetrical around the origo, and sampled. Good. The next part would be to analyze that. When we are analyzing the this back to the frequency space, basically, okay, we have the cutoff frequency, then we have the Nyquist frequency. Okay, what you would actually get there from sync. Okay, this is a multiplication in time. Multiplication in time is same as convolution in frequency. So if I plot this part, it will give me actually the on frequency space frequency space. It's a box. It's exactly that same box. Well, inverse Fourier transform or Fourier transform is the same function. But we actually, on time scale, we multiplied it with a box. The Fourier transform of a box, well, it's the same as inverse Fourier transform of the box, which is a sync function. But in this time, sync function would be on frequency space. All right, so we have the sync function here. And the convolution of those practically would give you the final, the amplitude response of that sampled and windowed sync function as that kind of thingy. So there is actually the flat part comes from the convolution of this box and that one, so it's mostly just constant, and then this after this edge, this one basically gives the edge effect of that one. Okay, so there's something a little bit wrong on this picture, meaning that we didn't get back exactly the box, but a little bit wider. Okay, so the transition bandwidth is wider, and then we also get some attenuation, well, some real attenuation. This one has the infinite attenuation. Here we have some such normal attenuation here. Okay, with a window of a box like that, the attenuation is roughly 20 decibels, not more than that. Okay. Well, it's also the same as the attenuation of a running average filter. You don't get much better than that if you look at the definition of the low-pass filter. So just wait a minute, I have wrong kind of view here. Okay, better. Okay, so that's the attenuation of, well, that window, which is basically the same as the average filter impulse response. So in that sense, this one is having the sink to transform this running average filter such that you actually have control of the cutoff frequency. Okay, so the sink function actually controls the cutoff frequency. By the way, I also need to scale this one, but I'll just leave it to the MATLAB part. But anyways, so we have a control of the cutoff frequency, which is good, but we have a lot of, well, we don't have that much of the stop band attenuation, which is bad. We can actually increase the stop band attenuation by smoothing the window. Smoother window size means that if we originally had this sink kind of from the box window, if we have smooth window, it has more power on lower frequencies and less power on higher frequencies. Yeah, since basically on box, in order to produce very sharp corner here, you must have, infinitely high frequencies with a still quite high the weight. Okay, so smoother window would do something like that. You will get wider transition bandwidth, but less power on the high frequency components. The cost is that it widens the transition bandwidth, but the difference is more attenuation on stop band. Good. All right, so smoothing the window basically gives you control on the stop band attenuation. Now we just need some way to basically control the transition bandwidth. And here we actually use the fact that when you multiply time, it's the same as divide of frequency. Yeah, they're inversely proportional, time and frequency. So it means multiplication in time, meaning wider sample of the sink would decrease the transition bandwidth. So getting better transition bandwidth, meaning increase the width. No magic there. Good. So that's how the window method on low-pass filter design would look like. All right. But I'm not happy yet. I'm hard to please kind of guy. Not really. But, so let's think about the system again on frequency axis. I'll just for fun put it on the of a system so that it actually has the both sides of the spectrum there, and just this is a low pass filter with a cutoff frequency of something like that. If we want to transfer this filter somewhere in here, well, it will also transfer it on the other side on over the some frequency FM would actually mean that we are convoluting this one with a just single frequency component, meaning we are modulating in time space. Single frequency component is simple. Well, this is still the h of n here, but if you multiply it with a cosine 2 pi fm times n, this part is just this single peak on the spectrum. Okay, so this one now is a band pass filter with a center frequency as fm. So that's the modulation. Modulation frequency, and that's also the center of this band pass filter. Couple of notes. Okay. Now our full width of that band pass filter actually is 2 times the cutoff frequency. It's basically on the both sides. Okay, that's nice. So we can actually use the modulation to transform these properties anywhere between 0 to Fn, which actually is also a kind of extra, well, special case. So if we are transferring this filter in here, well, we don't need to worry about those since those are the same frequencies, just the different phase. So basically this can be done by simply modifying the system with 2 pi times Nyquist frequency times n, which is, well, Fn was Fs over 2, so h of n equals cosine, no, not equals, times cosine of n times pi. Hey, wait a minute, that's the 2 pi. Sorry, Fs. Yeah, something was missing. Fs here, so you have 2 cosine of pi times n. This part here is just minus 1 to exponent of n, so it's plus minus 1, like that. So you practically just change every other sign on the impulse response you will get from low pass to high pass, or from high pass to low pass. Alrighty. So modulation gives you low pass to band pass or low pass to high pass. Another note about this filter, that's one place to make a simple mistake and lose a point. Now the bandwidth of this filter is FC. If that FC is here, but the cutoff frequency of this high pass filter is right here. Let's CC. Okay, so cutoff frequency is basically Nyquist frequency minus FC. Cutoff frequency of the high pass filter. So we are designing a high pass filter with the cutoff frequency somewhere in here. You need to actually take the bandwidth of this filter and design the low pass filter first like that, and then you transfer it to the transform it from low pass to high pass. Okay, so we have low pass, band pass, high pass. Only one fundamental type is now missing. Okay, how about band stop? Band stop filter would look like this. So that's one and two cutoff frequencies, and that's the band stop filter. That looks like a low pass. That looks like a high pass. And they are just added together. If you add filters together, basically it means that they are parallel. One is passing the low pass path and one is passing the high pass path. Low pass plus high pass. Just with the reminder, to make it easier to add these filters together, both systems should have the same order number. Same order filters. If they are different, then you need to basically just add just those parts which are overlapping. Okay, that makes it easy. Another thing, when you're adding systems, basically it also means that you add the stop band together. So basically you will get usually 3 dB 3 dB less the stop band attenuation as the original ones. Okay, good. Low pass to band pass, low pass to high pass, and then low pass plus high pass is band stop. 4 different filters with one single tool. Good. Just a curiosity, then of course we can have multi-band filters. Like the equalizers. For example, 200 Hertz, 2000 Hertz. That's the Nyquist rate. We might have 3 different bands. One for bass, another one for middle, and then third one for high frequencies. Yeah, but this is totally wrong. Usually you just, crank up the bass and and then maybe like that. Yeah. Until the bolt starts getting loose on your car. Excellent. So multi-band filter, low pass, band pass, and the high pass filters. Why you'd have only bass and treble the settings on normal car stereos? One reason they are very cheap. But anyways, the other one, well, you need just adjustment on those two, and keep that one basically to the volume. That's the same as the volume reference level. Okay, so you need only two adjustments, and this is the volume, which is always at 10. At least 10. All right, so that's basically how you make filters. Simple simple FIR filters. Another reason to the linear phase response would be also the easiness of adding channels together. So this is easy to implement filter also. If you had an IIR filter, you still would be adding, but remember what the IIR filter, the transfer function looks like. They're rational polynomials. And adding those is not that straightforward anymore. But in here, you can just add the, for example, this multiband, meaning that you have B times the low pass filter coefficients. Then you have the just that band pass filter coefficients. And then you have H, well, is that T? T times the high pass filter coefficients. So you calculate these coefficients and just have one single filter implementation for the data. Okay. But in IIR, you practically have to make 3 different filter implementations. So, yeah. So that's maybe another reason to work on with the FIR systems. But as I said, IIR systems, you get better amplitude response with the cost of nonlinear phase response, of course, with the less parameters, less coefficients. Okay. Let me show a couple of tricks on the MATLAB then. Where's my MATLAB? Okay, looks like a little bit big, maybe. All right, see. Now it should be more or less visible to the back row. Okay, so today's topic was about FIR filters. And how to work with them. Let's first start from generating the low pass filter. For example, running average filter at first, just for fun, unscaled running average. So I'll just have the scaling factor later on. So the impulse response of a running average filter. All right, so that would be RA equals just ones, and let's say make this, for example, 21 point running average filter. Wait a minute, I need to do it the other one. One row, 21 columns. Okay, the order number is 20. 20th order system. All right. So if I think this is the impulse response of the system, which means that then I can actually do the frequency response of this filter. Let me also define the sample rate just for fun. Sample rate, okay, and then let's take a quick look at what this filter looks like. FS. Frequency response of FIR system with the impulse response as RA. And this one comes from the fact that on difference equation you have 1 type Yn, 1 times Yn. And it looks like this. Okay, that's as good as the this running average system can actually come. And basically, this is the point which defines the low-pass filter characteristics. So can I actually do some modifications on that one? Line. Haha, yes I can. Let me add a line here. So basically, this is the level. Oops. Of course it does like that. That's the level of this stop band attenuation. It's the highest point on the frequency response, on the amplitude response, after the pass band. Okay, and that's not much. So for this type of filter, basically this is around 20 dB. Not much. Of course, it gets higher on when you add numbers, but it doesn't get much higher at the when you are doubling the number. It does not go even 3 decibels down. Okay. So that's, we can consider that as a window. First, I would like to check if I can make a cutoff frequency, which is now, well, cutoff frequency here is defined somewhere in here. You have minus 3 dB points. Okay. Yeah, it has a good, nice cutoff frequency, but on the other hand, the stop band attenuation that is not that great. But let's first fix the cutoff frequency, say up to 4 kilohertz. 4 kilohertz cutoff frequency, and use the sync to do it. So now basically we will have our system. Okay, let's see. Impulse. RA. Okay, let me think of it first. Windows sync. Okay, yeah, WS sounds like a good. So we have the RA, which is our sample window. Well, we can leave it out since all of those are ones. Got it? No, you probably already forgot what I'm doing here. Okay, I would actually forget it. So, just a moment. I'll just put those blackboard pictures. Oops. Blackboard pictures somewhere. Not there. All right. So I'm talking about. Hmm, I'm talking about this picture here. Too much light. Sorry about that. But anyways, so we have sampled sync, which is multiplied by a box. Nothing but the box. So we have sync of n times fc divided by Nyquist frequency. Maybe I should do the Nyquist frequency here. Fn equals fs divided by 2. So our windowed sync would be then just sync n would be from minus 10 to 10. Okay, let me do another thing. Indexes from minus 10 to 10. So basically that would be the same, the sampling indexes also for the running average. So same 20th order system and basically symmetric with the 0 point. Symmetric sampling. All right, and now we sample the sync equals sync n times n times the cutoff frequency 4000 divided by Nyquist rate. Let's see if I got it right. Maybe. And multiplying this with RA wouldn't do anything. Wouldn't do really anything at all. Okay, but we can multiply it with the cutoff frequency divided by Fn. But first, I would like to see what this looks like in here. So windowed sync. Ha! Excellent. So I got. This is about 4 kilohertz. I got the cutoff frequency on the right place. So that looks more or less somewhere at the minus 3 dB point. But as you can see, there's also the scaling factor. This is still, it's not unity scaled system. The scaling is simple. You basically calculate this by multiplying with this one here. Okay, and we didn't multiply this with RA because RA is just a just number of ones. But practically, mathematically, that's what happened. Good. So now it's unity gain system. Okay, but I'm not too happy about the smoothness of that system. For the getting a little bit smoother system, we can actually call a window function. And let's see, help. Let's take help on Hamming. Hamming window. Create, wow, returns an endpoint symmetric Hamming window. There are several different windows. Most common are Hamming, Blackman, one-hand. Then there's a Kaiser window, which is a window generator. You set up the parameters, and it basically gives you, different kind of windows. But the Hamming, Blackman, and Hanning are the 3 different, the 4 different windows, the most common windows. And they are very historic. Okay. For FIR systems, if you really want to go and optimize an FIR system, then you might use Saramäki routine to do it. So there's a signal processing professor in Tampere Technical University who has made the optimal window optimizer for FIR systems. That was in 90s. No, it was 80s when he actually found out or just was first to optimize it. Okay, good. So, but anyways, here we are. So I could actually use the Hamming windows. Halves. Okay, and we have already that window available. We just take the Hamming window with a length of that original system and transpose it. Okay, this is important. Transpose the window. For some reason, for historical reasons, MATLAB, these window generators are giving a row vector, while our system parameters are actually defined. Okay, that must be the column. No, the other way around. The system parameters are actually on single row, but these window generators are actually returning column vector. Okay, so that's why we have this small prime here to transpose. Otherwise, it gives you error message. All right, so now we have Hawes. Let's see what it looks like. The frequency response of Hamming window sync. Ha! Excellent. So compared to the previous one, let's compare. Where did I put it? Here. And there. Look the same. Wait a minute, I plotted the same thing, sorry. There, better. So now we have two different ones. Left-hand side is the original rectangular window shape, and the right-hand side is the new, with Hamming window shape. Okay, look at the stop band attenuation. On this Hamming, we are hitting 50 dB stop band attenuation. So that's 50. Let me put here a line to show it up. Okay, it's about 50 dB right there. Stop band attenuation. Then on the in here we have that about 20 dB stop band attenuation. Okay. However, the transition bandwidth is now wider. Transition bandwidth basically comes from, let's see, that's about 4 kilohertz, or from here and to here. So that's basically the definition points. So 3 dB defines a cutoff frequency, and then the stop band start frequency is defined by the last point on the transition bandwidth, which has the same attenuation as the highest point in here. Okay, so the transition bandwidth is also roughly 4 kilohertz. Okay, so but we are still missing one tweaking parameter. So we can control the stop band attenuation with the stop band. Not stop band. Let's see. We can control the cutoff frequency by selecting the sync, then the stop band attenuation by selecting the window shape, and then we can still increase the time, meaning take wider sample to decrease the transition bandwidth. So for example, if that transition bandwidth cannot be more than say 1 kilohertz, let's take a couple of values here. Okay, by typing G input, actually you can select values from a graph, but before doing it, you should actually select the graph where you do the measurement. So G input, well, that we already know, that's 4,000 hertz. Here we have another. Okay, click and enter. Okay, so that's 7,600. So our stop band start frequency is the first value of that answer there. So that's where the stop band starts. And the transition bandwidth is basically f stop minus our cutoff frequency, which was 4,000 hertz. There, okay. If we want to decrease this one, for example, to 1.5 kilohertz, for 1.5 kilohertz transition bandwidth, we need to multiply the time by factor TRBW divided by 1.5 kilohertz, 1,500. So this is the scaling factor for window size. About 2.4 times wider window. And we have 20th order system, so basically we need that's the new order number. New order. Oh, that's a bad historic sound on it. Okay. Okay. Order number to get 1.5 kilohertz transition bandwidth. Okay, TRBW there. Okay, order number is 48, meaning from minus 24 to 24. So, okay, the new indexes range from minus 24 to 24, or minus 23 to 23. This is not science, this is engineering. Remember that. So this should give us about the right transition bandwidth, which means that we need to generate the sink again, and we need to generate the black and window again. But let me just do it like this. HH low pass equals 4,000 divided by Fn. We still have this factor. We still have this sink, but we have sink from Nn2 times cutoff frequency 4,000 divided by Fn. Okay, that takes care of the transition bandwidth and the cutoff frequency, and then we need the Blackman window of, not Blackman, Hamming. I was using Hamming, right? Hamming window of 49 points, and that's it. New figure. So this one starts to look like a low pass filter. So we use the cutoff frequency on sync. We use the this window on to get the stop band attenuation, and we use the window width to get the transition bandwidth about 1.5 kilohertz. Good. So, and that's the low pass filter. Okay. Next, the low pass to high pass. Oh, band pass. Okay. To band pass transition. So we need a modulating frequency, and let me quickly look at. No, that's not a good one. Oh, I closed the window already. H low pass. There we go. So let's transform this filter so that the center of this filter is at 10 kilohertz. So center frequency, which is same as modulation frequency, is 10 kilohertz. And yes, the 10E3 is just fine. It's the kind of engineering notification. So H8 band pass equals. What we will do, we will modulate. So, okay. Not that one. There. Doesn't show up too well, but anyway, so we are modulating with the cosine function. Why cosine? Well, there's a very good reason. It has less zeros than sine when you have a symmetric point. And basically, sometimes with the sine, you are losing a little bit too much of the energy from the filter. So cosine is a safer modulator. So low pass filter is basically two pi. Okay, something's missing. Divided by sampling rate. Yes. Yeah. Or NN2 times TS. It's a sampled cosine, nothing more, and multiplied element by element with our low pass filter impulse response. Whoa, what happened? Okay, and then we will just do the frequency response of that, maybe on another window. I hate when that happens. Figure band pass. Ta-da! And we are losing the power as by a factor of 2. And why that one is happening? Well, we are splitting the spectrum on both positive and negative side of this spectrum. So this one is just half the power. Or another way of thinking it, we multiplied the signal with cosine, with basically power of 0.5. Okay, so let's scale this one for low pass to band pass. You will scale this by multiplying by a factor of 2. Okay, now it's unity gain filter again. And the width of the filter is 2 times the cutoff frequency of the low pass filter. So lower cutoff frequency is the center frequency minus this original low pass filter cutoff frequency, and the high cutoff frequency is the middle the modulating frequency plus the original cutoff frequency. There. So that was how to make band pass filters from low pass filters. Third one is the special case of from low pass to high pass. Okay. HP equals HH low pass multiplied by modulating of cosine pi n, or minus 2 to the power of, okay, dot power of nn2. There. So that's basically how you make the power of -1 with the vector which holds the these numbers. Another, wow, why is doing that? Well, maybe there's a good reason. But anyways, that's how you do the modulation with the -1 1 -1 1, or cosine pi times nn2 would do exactly the same thing. All right, so let's add some pictures. And this was high pass filter, and it looks like that. Oops. There you go. So now the cutoff frequency of this high pass filter is something like, well, 22,050 minus that 4 kilohertz. So bandwidth is the same as the original cutoff frequency. On the exercise, there is actually, I'm given the cutoff frequency of the high pass filter. Okay. So that was the high pass. Just to make it a little bit more interesting. Okay, I think that's interesting enough. So then the band pass. Band stop, sorry, band pass we actually had already. So band stop is same as low pass plus high pass. And I'm just cutting some corners here. So HHBS is low pass plus high pass. As long as the size of the vectors is the same, or actually the order number is exactly the same, then you can do it like that. And one more picture. There you are. And of course, well, that's kind of, I was lazy. Usually it's not that symmetric. Basically, you need to design this one separate from the low pass part. Another thing, okay, I mentioned about the losing some stop band attenuation. Let's put this one next to, for example, the original low pass filter. There. Okay. As you can see, well, just barely see, this one is evidently lower than that minus 50 dB line here, and these are just right at the 50 dB line. So we lost some of the stop band attenuation because we are adding the stop bands together with phase. Okay. So let me see, what did we have? We started from low pass. We got band pass by just modulation. We got high pass. Well, that was also modulation. And then we got the stop band. Those are the fundamental filter types. Good. Let me take a quick look at the exercise. Not that one. Wait a minute. It was that one. Okay. FIR filters. There, and then we have the exercise template right here. Just to make sure what you should be doing today, or well, at least until the next Monday. Okay, compare the amplitude responses of different window shapes. Okay. Now you are basically comparing Hamming, for example, with Blackman and one-hand filters. There was 3 other window shapes on that help file of the Hamming. Select one of the previous windows, high wide window you need to take in order to change transition band by factor of. Okay. So basically you need to so the new transition bandwidth would be the old one multiplied by 0.SSS. You just calculate how much wider window you need. Okay. Third one is a design a low pass filter. They are the parameters. Excellent. Just those. So you need to start with the cutoff frequency. Then another one. Okay, there is a stop band attenuation requirement. You must select an appropriate window shape for that one, and then transition bandwidth. You will then last select exactly or tweak your this window width. You start with arbitrary window width, and then you just scale that one so that you get your filter design to match these requirements. Okay, from from low pass filter to band pass filter. Then, okay, high pass filter. Remember, the trick here is actually that this is the high pass filter cutoff frequency, meaning this one. Not the bandwidth of the high pass, but cutoff frequency from 0 to that one. But on the design, you need the bandwidth. Okay? Then I have a noisy voice sample, do the spectrum analysis. Oh, did we do yet last time some spectrum analysis on the third exercise? Yes. Okay, good. Okay. Spectrogram of that one, finding the signal level, noise level. Was that also last time? Maybe. Should I? Maybe. And define the filter requirements. Okay, on the sixth exercise, there's a voice and noise. If I remember it correctly, it looks like something like that. There's some voice here, and then it has very high the noisy part. You need to figure out how much you need to attenuate the noisy part. and basically pass the information as it is. Okay, so do the spectrum analysis and then design the filter so that it passes that voice but removes enough of that noise so that you can hear the discussion. It might be all, well, for me, when I listened that voice sample first time, I noticed, oh, this is so obvious. No, everyone would know that, and so I added some extra noise there. It's not that obvious actually. It depends a lot from your culture, but I can give you a hint. It's not Finnish. The discussion in there is not Finnish. Okay. What else? Yeah, and define a filter to, requirements to reduce the noise. Yeah, that's basically from the graphics. You have the spectrum. How much you need to attenuate the stop band? How much you actually have there allowance for the pass band? So basically, what is your transition bandwidth requirement? Some of that you will lose in any case, but how much you can tolerate. You can also there use intuition in which frequency range discussions are usually. Well, it depends, of course, if it's male or female or lower tone or higher tone, that kind of stuff. But well, still they are about the same. Okay. And then 8, design an FIR filter to match it. Verify the design. And last one is to filter the signal to try to hear what language the person is talking. Okay, one small hint. Usually when you start the filter and you have time-based signal, the start of the filter, you might actually get some extra bang on the beginning of the filter. You can either make a time-based window to get rid of that bang, or just leave it there and turn up the volume and let the amplifier saturate. Okay. But anyways, I recommend using headphones to listen about that talk. Usually you have all sorts of noise in wherever you are working on. So headphones would help on recognition of that voice. A lot. Good. All right. So that's the 4th exercise about finals impulse response systems. So first you just design a couple of filters, and then you would analyze a voice sample and design a filter to reduce the noise level. Easy. About next week, let me show something. Next week we have the topic would be IIR filters, but I'm in Spain next week. So it means that the deadline for the 5th exercise, which is the last exercise, will be kind of funny. It's April 30. Yay! May Day Eve. But, well, it's 2 weeks from now, but I will be present again on 23rd to give the tutorial. There is also a chance that if you want to, take a head-up start, there's the last year's stuff also available as video. I think there are, let's see. Yeah, that's the last fall, the DSP lecture, what I have there. So take a look at that one if you want to take a head start. Okay, the video over the lecture and of course also the lab tutorial is there. But the deadline for the exercise is April 30, and I will be here on April 23rd, but not next week. April 16, I'll be abroad. Okay, thank you. That's my part of the show today.